Welcome to the chapter on physics basics. Understanding the fundamentals of physics is crucial for mechanical engineering students. In this chapter, we will cover the basics of mechanics, thermodynamics, and fluid mechanics. Mechanics is the branch of physics that deals with the motion of objects and the forces that affect that motion. It can be divided into two main subfields, kinematics and dynamics. Kinematics is the study of motion without considering the forces that cause it. Key concepts include displacement, velocity, and acceleration. The equations of motion for constant acceleration are v equals u plus at, s equals ut plus 1/2 at squared, and v squared equals u squared plus 2as. In these equations, v is the final velocity, u is the initial velocity, a is the acceleration, t is the time, and s is the displacement. Dynamics is the study of the forces and torques that cause motion. Newton's three laws of motion are fundamental to dynamics. Newton's first law, also known as the law of inertia, states that an object will remain at rest or in uniform motion unless acted upon by a net external force. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This is expressed as F equals ma. Newton's third law states that for every action, there is an equal and opposite reaction. Consider a car that comes to a stop from a speed of 20 meters per second in 5 seconds. To find the acceleration and the distance covered during braking, initial velocity is 20 meters per second, final velocity is 0 meters per second, time is 5 seconds. Using the first equation of motion, v equals u plus at, we get 0 equals 20 plus a times 5, which simplifies to a equals -4 meters per second squared. Using the second equation of motion, s equals ut plus 1/2 at squared, we get s equals 20 times 5 plus 1/2 times -4 times 5 squared, which simplifies to s equals 50 meters. Thermodynamics is the study of energy, heat, and work. It is essential for understanding how engines, refrigerators, and many other systems operate. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transferred or converted from one form to another. Mathematically, it is expressed as delta U equals Q minus W. In this equation, delta U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. Entropy is a measure of the disorder or randomness of a system. Consider heating 1 kilogram of water from 20 degrees Celsius to 100 degrees Celsius. The specific heat capacity of water is 4.18 joules per gram per degree Celsius. The heat required is given by the equation Q equals mc delta T, where m is the mass, c is the specific heat capacity, and delta T is the change in temperature. Substituting the values, we get Q equals 1000 times 4.18 times 100 minus 20, which simplifies to 334,400 joules. Fluid mechanics is the study of fluids, both liquids and gases, and the forces on them. It is crucial for understanding how fluids flow and how they interact with their surroundings. Fluid statics deals with fluids at rest. The key concept here is pressure, which is defined as force per unit area, expressed as P equals F divided by A. Fluid dynamics deals with fluids in motion. The continuity equation and Bernoulli's equation are fundamental principles in fluid dynamics. The continuity equation states that for an incompressible fluid, the mass flow rate must remain constant from one cross-section of a pipe to another. Mathematically, it is expressed as A1V1 equals A2V2, where A is the cross-sectional area and V is the fluid velocity. Bernoulli's equation states that for an incompressible, frictionless fluid, the sum of the pressure, 1/2 the fluid density times the velocity squared, and the fluid density times gravity times height remains constant along a streamline. Mathematically, it is expressed as P plus 1/2 rho V squared plus rho GH equals constant. Consider water flowing through a pipe with varying diameters. If the diameter at point 1 is 0.1 meters and the velocity is 2 meters per second, and the diameter at point 2 is 0.05 meters, we can find the velocity at point 2 using the continuity equation. Using the continuity equation, a1v1 equals a2v2, we get pi times 0.1 squared times 2 equals pi times 0.05 squared times v2, which simplifies to v2 equals 8 meters per second. This chapter has provided an overview of the basics of mechanics, thermodynamics, and fluid mechanics. These principles form the foundation for many topics in mechanical engineering.